So in the last video, we talked about computing arc length in terms of dy, and we had this generic picture that we looked at. So say that we have our function that looks like this arc, and we want to know the length of the distance from x1 to x2. We had this triangular picture, and by Pythagorean theorem, we know that the length of this side L is going to be the square root of each of the pieces dx and dy square rooted. And last time, we decided to factor out the term delta x squared from each of these pieces. That left us with this formula for L. L is equal to the square root of delta x squared times 1 plus dy dx squared. It's what it ends up being when we integrate, which is the derivative of our function. And so we ended up with this arc length formula. The thing that I want to point out is that everything for this formula is in terms of x. So our function itself, our function f, is f of x. Our bounds are in terms of x. They go from where x equals a to x equals b. And our differential back here is a dx to remind us that we're splitting this up in tiny little pieces along the x-axis. Well, suppose that we had a function that wasn't a function of x, but was a function of y instead. We can rewrite the same thing, but in terms of y. So let's go back to here. Our length L, no matter what, is going to be, by Pythagorean theorem, the square root of delta x squared plus delta y squared. But this time, I'm going to factor out a delta y, meaning that I'm left with the square root of delta y squared times delta x divided by delta y squared plus 1. Right? So this is the opposite of the distributive property. If I were to multiply this through, I would see that I would get those pieces. And when you do that, why would we want to do that? What is this delta x, delta y? This can simplify out, right? This becomes delta y times delta x divided by delta y squared plus 1. And if I want to compute the arc length in terms of delta y, this would only be applicable if my function is something that looks like g of y, which is equal to my variable x. And so here, instead of dy dx, this dx dy is the derivative of my function in terms of y, right? And it would be whatever the derivative is. So that means if I want to look at the arc length in terms of y, my new formula is going to be exactly the same, but everything is with y's instead. So my bounds are going to go from where y equals c to y equals d. I'm using these letters to note that my x bounds are down along the x-axis, whereas these bounds are talking about bounds along the y-axis. So if I'm summing up along the same interval, it would be from this y value to this y value. And just like before, we're summing up each of these triangular pieces, so we'll end up with, by this formula, we'll see that it's going to be the square root of g prime of y plus 1. This g prime of y is squared because it's my dx dy times dy. So this is my differential in terms of y, and this is telling me that I'm breaking it up into pieces that are little slices along the y-axis instead of the x. Let's put this formula to use. So I'll write in terms of y. And obviously I could flip-flop the places of these, but these are very similar formulas, but the pictures are going to be very different. Before we do that, let's look at an example. So let's say that I want to find the arc length of my function g of y equals 4 minus y squared in the first quadrant. So let's start by drawing a picture of this. So what does this function g of y look like? It's tempting to think that it looks like, well, it has a negative something squared, so that we tend to think of as an upside down parabola, but because this is now the inverse function that I've switched my x and my y's, I can plot points to be able to check what this function looks like. Your calculator isn't going to be able to do a good job graphing this because your calculator by default has x as your input value, and typically we're going to keep our axis as x and y axis. So in this function, if I let my y equal 0, my x equals 4. If I let y equal 1, I get 1 squared minus 4, my x value is 3, and when y equals 2, 2 squared minus 4, my x value is 0. And this is enough to give us an idea of what this function looks like. When my x value is 4, y is 0. When my x value is 3, y is 1, y is 2. And really what this is, oh, I should have flattened this out more. It's an arc of a parabola, and it's a parabola that's been laid on its side. If this function were plus or minus, it would continue this way because it's not really a function in terms of x. But we only want to know the arc length in the first quadrant. That's this quadrant here. So this is the point 0, 2, where my x is 0 and my y is 2, and this is the point 4, 0. So let's set up this integration. I know that I want to find arc length, and the clue that this arc length is going to be in terms of y is the fact that my function is written in terms of y. If I wanted to, I could solve this, I could set this equal to x, and solve this for y, and then plug that function of x in. Instead, we're going to do all of this in terms of y. So the first thing that I want to ask is, what are my bounds on y? And in this case, we're looking from our y value equal to 0 down here up until, which corresponds with this point, up until my y value equals 2 up here. And this is a little different than what we would think about. So my bounds are from y equals 0 to y equals 2. I'm not worried about what the x components are, and it's because I'm breaking each of these pieces up into little dy components. So my arc length, I think I call it L, is going to be from y equals 0 to 2 of the square root of, I'll write out g prime of y squared plus 1 dy. And we can do a little scratch work. This is pretty easy to find the derivative of, because g of y is equal to 4 minus y squared. That means g prime of y is going to be equal to negative 2y, and g prime of y squared, I'm going to square this. That means the negative 2 is squared and becomes 4, and the y is squared and becomes y squared. So that means that this arc length is going to be from y equals 0 to 2 of the square root of 4y squared plus 1 dy. So the task of integrating this is a little bit harder than what we would want. There is a trig substitution that you could do. You could let y equal tangent x. I would have to pull out a 4 first, and then I think it ends up being 1/2 tangent x. That's one trig sub, but then it turns out you need a whole sequence of trig subs and integration by parts, and it's much, much messier than what I want to do right now for this example, because we're focusing on arc length and not really difficult techniques of integration. So I'm just going to get a numerical approximation on my calculator. Recall that I'm going to go to math, I'm going to go down to where it says integrate, and the function in this case is the function 4y squared. Whoops. Notice that in this calculator, when I do the variable key, it doesn't give me the option to turn this into a y. I'm allowed to use an x in this case because I'm going to make sure that I integrate it with respect to x. I'm using sort of a dummy variable or a u substitution idea here. And it does matter whether it's a dy or dx when we set up the problem, but once you get down to the point that you're integrating, it really doesn't matter what the name of this particular variable is, as long as the bounds match the function and match the differential. So I'm taking this innermost function and raising it to the 1/2 power. That's the same thing as square rooting, comma. I'm integrating with respect to x in this case. and my bounds are going from 0 to 2. When I close this parenthesis, it gives me my value. So this is approximately equal to 4.647. And looking at this picture, that makes some sense because this distance is 4. We would expect that this distance would be larger than 4. So let's continue on, just like before, how we also computed surface area in terms of dx. Now let's do it in terms of dy, and I have a couple of pictures to compare. So last time, maybe let's just focus on this picture. Last time we had our function f of x, and we thought of a whole series of bands, and each of the widths of the bands was given by L, which is the arc length of this function. And we decided that the surface area of one band was going to be 2 pi r L, and r in this case is the radius, and the radius is the height, which is given by y or f of x for this function, which led to this formula. This is just review. But let's see, so maybe this is a misleading title. So this example is in terms of dx, right? Because I have dx's here. What happens if we want to do it in terms of dy? It's going to be a really similar picture, but all of our variables are going to flip-flop. So again, I would know that I would want to do my integration with respect to y because my function in this case is a function of y instead of a function of x. And it means that for each one of these little bands, the same thing is true, that the area here is still going to be 2 pi r L, but our r and our L changes slightly because our r in this case, it's this width here, which is our x value, and x in this case is given by g of y. Maybe I should say g of y. That's our distance over in this case, rather than talking about a distance up. So that means that here, our area is going to be equal to 2 pi, our radius we just said was g of y, and then L is going to be this little arc length along the end, and we're going to use the formula that we generated just previously. It's going to be g prime of y squared, plus 1. So that's the area of this one piece. Maybe I should have said dx dy squared plus 1 square rooted, because we haven't yet taken the integral. So these are equivalent statements, with this one being the limit inside of the integration. So what does that mean for our final formula? So if I want to know the surface area of this shape rotated around the y-axis, it's going to be 2 pi, and we're going to sum this up as our y values go from a to b, so I'm going to emphasize that by writing my bounds are going to be in terms of y. My function is g of y, and my arc length L is going to be g prime of y squared plus 1 dy. And again, this dy at the end is telling me that I'm splitting up these bands in terms of y rather than splitting them sideways in terms of x. So finally, let's look at an example. So we're going to find the surface area of g of y equals e to the y rotated about the y-axis from x equals 1 to x equals 2. So let's draw a picture of what this looks like before we go too much further. So what does the function g of y equals e to the y, what does that function even look like? I know what the function e to the x looks like. It's a function that's an exponential function that starts low and goes upwards. But this is not the function e to the x. It's the inverse of that function because I flip-flop the positions of the x's and the y's. And it turns out that this function is going to be actually a natural log function, and you can solve it by solving for one of the variables. And it goes through the point where x equals 1 and y equals 0. So that's what the function is. I'll label it g of y. And now we're going to rotate it about the y-axis from x equals 1 to x equals 2. So we've already found here, let's see what happens when x equals 1. G of y is x. So when g of y is equal to x, we'll see that when is e to the y equal to 1? In order to solve for y, I'm going to take the natural log of both sides, and I get the natural log of e to the y is the same thing as just y, which is the natural log of 1. So that means that y is equal to the natural log of 1, which is 0. And that's one bound, and then the other bound is when x equals 2. So when e to the y is equal to 2, I'm going to again take the natural log of both sides, and we see that y is equal to the natural log of 2. And I don't really know what the natural log of 2, I could plug it into a calculator to find the exact value. Really, it's the exponent that you put on e to get a 2. It's a fractional number that I want to compute a decimal approximation for. So that means that this point up here is the point 2 comma natural log of 2. So we're going to take this part of the curve and we're going to rotate it around the y-axis. We're going to get sort of a cylindrical looking thing like this. And we want to know what is the surface area of this shape. And we're going to break it up into dy bands. So why are we doing this in terms of dy? There are a number of hints. So the first thing is the fact that we're rotating it around the y-axis. And even if the name of the function was given as g of x, if we rotate around the y-axis, there's no way around it that we're going to have to do it in terms of dy, because it wouldn't make sense to try to split up our little bands. The heights of these bands are being sliced thinner and thinner in the y direction. So if it was given with a name in terms of x, we would have to convert it into a name in terms of y. But at this point, we're ready to set up our integration, because we have all the pieces that we know. We know that our bounds, so this is our surface area, our bounds are going from where x equals 1 to 2, but because we're integrating with respect to y, it's where our y values are going from 0 to natural log of 2. And so these are our bounds on y, and then we're going to multiply that by the radius, and the radius is our function g of y, and the radius in this case then is e to the y. And then we're going to multiply it by L, which is the square root of g prime of y squared plus 1 dy. So this is our radius, this is our L, and because it's in a circle, we also have to multiply it by 2 pi, and that's something that, of course, I'll write that in front. I failed to leave space for the 2 pi. So let's do a little side work. G prime of y is the derivative of our function, which thankfully is a pretty easy derivative. G of y is e to the y, so our derivative is e to the y as well. And so that means that g prime of y squared is e to the y squared. I'll write this out because this is an exponent property that people frequently do incorrectly. And so that means that our surface area is going to be equal to 2 pi times the integral as y goes from 0 to the natural log of 2 of e to the y times the square root of e to the 2y plus 1 dy. Now again, this is something that looks so close to being a u substitution, something that we would have a technique of integration to be able to account for. It turns out you can try a couple of different u substitutions and none of them will work. The obvious choice would be something like u equals e to the 2y plus 1, but then our du in this case the derivative of this becomes 2e to the 2y plus 1 down in the corner dy. And we don't have an e to the 2y. That's the same thing as e to the y squared. We only have one of them. And so this u sub is not going to work. In general, when doing these arc lengths or surface area functions, it's very difficult to have a closed form for the antiderivative. So instead, we're going to do a numerical approximation on our calculator. We're going to integrate. Our integral is this function, e to the y times e to the 2y plus 1, all square rooted. Let's make sure that my parentheses are correct. I have the e to the y term, and then I have that term. Okay, plus 1. Great! Because it's easy to miss a parenthesis and then the function won't work out correctly. In the best case, they just say it doesn't work. In the worst case, they give you an incorrect answer. So we're integrating with respect to x in this computation because we've already set it up correctly. The computation is correct. We don't need the picture anymore. And our function goes from 0 up until the natural log of x. And of course, I can't find natural log on my calculator. But if I were to find natural log, I could plug it in and it would give me an answer. So, of course, it's because it's natural log of 2. And enter. It thinks for a little bit and it tells me that this arc length is about equal to 1.81. And again, this is actually at a height of about 0.69, so it makes sense that this distance is traveling 1 unit in this direction and then 0.69 up in this height. That means that it makes sense that that total answer is about 1.8. Although, that's just the integral. I forgot to add the fact that this is going to be 1.8 times 2 pi, of course, because we're rotating it around. So I need to take this answer and multiply it by 2 and pi. So this computation was a modification of the arc length, but in addition to that, we have to rotate it all the way around, and that's why we get our 4.355 for the entire surface area.